Good evening, ladies and gentlemen. I'm Pauline Davies from the Beyond Centre, and I'm going to introduce tonight's moderator, Marcelo Gleiser, and he helped organise the event, and he's the Appleton Professor of Natural Philosophy and Professor of Physics at Dartmouth, where he also directs the Institute for Cross-Disciplinary Engagement. And he's also the author of 5 popular books on physics. So he's going to introduce tonight's speakers and moderate the question and answer session. But meanwhile, just before we start, could I ask you to turn off your phones, please? Thank you. Marcelo.
Great, thanks, Pauline. Hi, good evening, everyone. Thanks for coming. So as Pauline said, my name is Marcelo Gleiser, and I'm also a theoretical physicist, like one of our speakers. So my role tonight is to moderate what I hope will be a very interesting conversation on a subject which is profoundly commonplace and profoundly mysterious: time. Right? I mean, everybody knows about time, and we all talk about time, and we never have any time. And what the heck is going on with time, right? I mean, and it turns out that one thing that I observe is that the older you get, it seems that time goes faster, right? What is this about? Is this anything, any relation with the physicist time or not? So what we do at the Institute for Cross-Disciplinary Engagement, aka ICE, I always call it the good ICE, you know, to differentiate it from other kinds, is that our mission is to bring the sciences and the humanities into what I call constructive engagement, right? So the idea is that there are questions that we deal as a modern society that require not just a scientific or a humanistic approach, but really a constructive combination of both of them. And the nature of time and other topics that we have dealt with before, for example, the nature of intelligence and consciousness, and the nature of faith and the relationship with science. These are questions that you really need to come into a plurality of perspectives in order to make sense of what's going on. So time is a very adequate one, and usually what we have is a scientist and a humanist that talk about the same topic. The way we organize the evening is they will each talk for about 20 minutes, and then I will ask them questions, and they can ask each other questions for another 20 minutes, and then we'll open for Q&A from the audience, okay? And you can ask your questions. And after that, for those of you who registered, there is a follow-up workshop where you can have some more questions to ask us and to engage in conversation on these topics. Now, one of the things that I ask you to do in this evening is that because these events cost money and we are sponsored, we actually have a survey that I really would very much ask you to complete before you leave. If you don't have pencils, we have pencils to give you. All you have to do is mark the X's in the right spots, and we do a quantitative survey of how relevant the evening is for you and how important it was for you as well, okay? All right, so I will introduce the speakers now, and then I'm going to show you a very short video introducing the institute that we work on, ICE. And of course, let me just mention, which is very important, that this evening is done in partnership with the Beyond Center. So it's really a joint venture between Dartmouth and ASU, which is very exciting. Okay, so one of our speakers is Jimena Canales. She grew up in Mexico, and then she came to the United States, where she did a master's and a PhD at Harvard in the history of science. And then she stayed at Harvard teaching for many years, and then she moved to the University of Illinois with a position called the Thomas Siebel Professor of History of Science, and then she returned recently back to Cambridge. She's the author of many technical articles in journals, and also of 2 books. One is called A Tenth of a Second, and the other one, which is the one that is, well, they're both about time, funnily enough, but the other one, which is the one that is more central to us tonight, is called The Physicist and the Philosopher. And this book made a lot of noise when it came out. It received a lot of praise. It was voted best science, one of the best science books of 2015 by Science Friday NPR, by Maria Popova's Brain Pickings. It was also called the top read by The Independent, top science book 2016 by The Tablet. And she has also written many essays for The New Yorker, The Atlantic, Wired, BBC, and other venues, right? And what she's going to do in her book, this book about the physicist and philosopher, the physicist is Albert Einstein. The philosopher is Henri Bergson, who was the biggest intellectual superstar in Europe in the 1920s, much more famous than Einstein was at the time, believe it or not. And the two sat together in some conversations in Paris about the nature of time that were, in a sense, to change our understanding of what time is. And she's going to talk about that. Our other speaker may be familiar to some of you since he's a local celebrity. So Professor Paul Davies, he's a world-renowned theoretical physicist. He works in cosmology, in astrobiology, and also in astrophysics, in the theory of black holes. He has written many, many books, and he's also the Regents Professor here at ASU and the director of the Beyond Center for Fundamental Concepts in Science. He has written 3 books explicitly on time. One of them, a more technical one from 1974 called The Physics of Time and Symmetry, and then 2 more popular ones called About Time from 1995, and then the one that I would love to know the answer is How to Build a Time Machine from 2001. He may not even be here right now. I'm not quite sure. You know, he may be using it. He's won many awards, including the Templeton Prize, and also the Kelvin Medal and the Faraday Prize, which are given to people who make a real big difference in the public understanding of science. So before I bring you to stage, you may want to play the video, please, and then we'll all sit together. Thank you.
The world is a complex place, a network of flowing information and changing patterns, where forces known and unknown generate the most sublime beauty and the most terrifying destruction. The world inspires wonder and doubt, and we humans try to make sense of it all, creating stories, theories, symphonies, and poems. I am Marcelo Gleiser, director of the Institute for Cross-Disciplinary Engagement at Dartmouth, or ICE. On behalf of all of us at ICE and our partners, I invite you to be a part of our institute, to be a part of this very essential conversation. What is the nature of reality? What is the future of humanity? Will machines think? Will and should we become immortal? Is there free will? Are we alone in the universe? Can science be a path towards spirituality? ICE was created to address these issues and establish new bridges between different ways of knowing. Our mission is to overcome old bigotries and facilitate a constructive dialogue between intellectuals and the general public, creating a community of citizens concerned with the common good, engaging experts, promoting public dialogue, and offering open access courses. One thing is certain: the hardest questions ask for different viewpoints, for a cross-disciplinary approach, for intellectual openness. The sciences and the humanities need one another now more than ever, and we need them both.
So everything that we've done so far, including the videos of all the other public lectures, are on our website, and you're welcome to come and watch it at any time you want. Okay, now without any further ado, please, Jimena and Paul, join me, please. Thank you. And just for the proceedings, we decided that Jimena will start.
Great, thank you. Thank you all for being here. Thank you, Marcelo, for a wonderful invitation. Can you hear me? Yes? Okay. No? Is the microphone on? There we go. Okay, here we go. Thank you. So, as Marcelo said, I'm a historian of science. I've been studying science for about 20 years, mainly from a historical perspective, although I'm very interested in contemporary science. And I started my career writing my first book, which is this book about a tenth of a second, a history. And I joke that I wrote the longest book about the shortest time period in history. And it's about why we started to be concerned with measuring short periods of time that don't really matter for our everyday lives. And this is the tenth of a second. So the book starts around the middle of the 19th century when there was this French astronomer, Francois Arago, who claimed that clocks that measured the tenth of a second were no longer a vain luxury, but that they should be adopted in science. And then after that, we see a race to measure even shorter periods of time. And I believe we're still in that race. The ability to measure short periods of time and to have accurate standards of measurement since then became a mark of civilization and civilized cultures. So that was the main interest in my book. And again, I was, as a historian, a young historian, when I started writing my book, I read a lot of political history. I read about presidents and kings, and I thought that none of the history that I was reading and most of the history that I was being taught in my classes didn't explain some of the essential texture of modernity. And that's basically why our fingers are now in keys, why our eyes are tied to screens. How do these systems in which we have a stimulus, the stimulus goes through our nerves, we react within a tenth of a second. That's the importance of the number that I was interested in, and have a reaction. Anything from stepping on a car brakes, but why did the systems came to symbolize modernity, and why did they become so prevalent? So I look at these timekeeping instruments, I look at the history of reaction time, the history of astronomy, together with the history of experimental psychology. In my view, could help us understand the texture of modernity, the sensory motor order of modernity. Why our eyes and fingers end up in certain places, manning certain devices and not others. And towards the end of the book, as I said, it takes place mostly in the 19th century. I knew from my research, I always knew that there was one of the most famous philosophers of the late 19th and early 20th century was Henri Bergson, a French philosopher. Just to get a sense of how many of you have heard of Henri Bergson before? Not so many people. So he was basically more famous than Einstein, and he was an expert on time, among other things. He wrote a book in 1907 called Creative Evolution that made him world famous, and he was a real public intellectual, one of the first intellectuals to have a radio program. He hobnobbed with heads of state. He was influential in convincing President Wilson to join the war. He's rumored to have created one of the first traffic jams when he gave a lecture in New York City. William James, for example, admired him, and I remember when I started studying Bergson, people would say, well, he read William James. I'm like, no, William James read Henri Bergson. So I knew of this figure that was largely unknown today. There was one conference in Berkeley, probably about 15 years ago, but there hadn't been a major conference on Henri Bergson in the last 50 years in the U.S. And I bumped into this document where there was a transcript of a meeting where Einstein was giving a talk in Paris, and Henri Bergson was in the audience. And I just couldn't believe. I thought this was a historical treasure, and I thought that there had been many, many, many people who had written about this. We all know Einstein's importance, and some people knew of Henri Bergson's importance. So what did they say to each other, and what happened in the meeting? And to my surprise, there wasn't any book-length account of their meeting in April 6, 1922. So I decided to dive in and to figure out as much as I could about that day, and to answer some of the questions I had. You know, why do we not know why is Bergson so little known today? And it's really a fascinating story. Einstein had become a very famous physicist in 1919 after an eclipse expedition confirmed his general theory of relativity. Basically, it confirmed that gravity bent light around the sun, and some British astronomers, Dyson and Eddington, measured this, and they did one of the first sort of announcements of science by press release, a big event in which they proved, and the way the paper is constructed, this event could have been explained in many ways. There were many other people who had been interested in the possible question of gravity bending light waves. But the way that the paper was presented, there was really an option that didn't explain. There was no change at all. Gravity did not affect light waves. There was another option where it affected light waves to a certain degree, and then there was a third option where it bent the light waves to the degree predicted by Einstein, and the results matched number 3. So the newspapers all over the world covered the incident, and Einstein went from being a well-known, respected, but controversial physicist to being a worldwide star. He was chased around by photographers. He wrote that at that time every child in Berlin could recognize him from photographs. And he even went at one point, he was his face was more recognizable than Hollywood stars at the time. And this is the 19-teens, the beginning of Hollywood, the beginning of the movie industry. And there's an incident in which he goes to California, he goes to the movies, and the biggest Hollywood star at the time was Mary Pickford, this woman. And they stopped the movie because Mary Pickford wanted to say hi to Einstein, and Einstein shook her hand and didn't know who she was. So there's this very interesting reversal at the time of the role of the scientist as a public intellectual when they became, and scientists had given, you know, Helmholtz, Pasteur, Darwin, they were very known people, but they weren't really newspapers. And this is the time when the daily press becomes one of the venues in which people learn about science. And it's after World War I, and readers are very eager to hear wonderful stories, not only stories about carnage and devastation and the bad Germans and the bad French guys. So science starts taking this role. Einstein is invited to go to France to speak, particularly because he's a pacifist, and he has written against the militarization of Germany. And he has been German Jew who works in Switzerland. He has a complicated relationship. He's very friendly with the British astronomers who ran this eclipse expedition to Proven. And there are people in France who really want to support his theory. Surprisingly, they're philosophers more than physicists. So Einstein is not invited to talk to the Société de Physique. He's invited to give some talks at the Collège de France, and also, more importantly, the meeting that I'm interested at the Société Française de Philosophie. So on April 6th, 1922, and you see so there's some photographs of this incident of people just trying to get in, trying to see this great star. He gets to Paris on train. He arrives to the City of Lights. He arrives at the Gare du Nord, and there are many journalists waiting for him. So he escapes the other way through the other tracks, going through where it says, you know, do not enter, to avoid. So this is a huge event, and he starts speaking at the Société Française de Philosophie. Very bad French. He doesn't speak French. We all know this myth that Einstein was not good at school, and it's pretty much a myth, except when it comes to France, to speaking French. He really did not like the language. One of the first references that I found of Einstein talking about Bergson was that a friend of his wanted to read something in French in order for them to get better at it. And Einstein says, no, I'm not going to read that flaccid Bergson. And many years later, here he is. His correspondence also shows that he's very nervous about the talk. He's very nervous about speaking in French. He has a good friend, Paul Langevin, who developed what we know now as the twin paradox. And the journalist said that Paul Langevin is whispering the answers to Einstein that evening. The evening, there's a complete transcript, and this was my excitement as a historian. You know, on top of everything, here I have a transcript of everything they said. The tone of what they say is conveyed in parentheses, sometimes in the transcript. So the evening starts well with a short introduction by Einstein, and then they open up the discussion. And then Einstein says something that serves as a detonator that evening. And he basically says, and Henri Bergson is in the audience, they're talking about the nature of time and what is subjective time. And he says, il n'y a donc pas temps de philosophes. There is no time of the philosophers. And people start sort of nodding each other, and the organizer says, you know, it'd be nice if Bergson speaks. Bergson says, I did not come here to speak, but I will respond. And he responds in about 15 minutes to this incendiary claim that there is no time of the philosophers. And I will, if I have time, I'll say a little bit more about the actual, what was at stake that evening and with that response. But let me backtrack a little bit and talk about what Bergson found so offensive about this and what happened afterwards. So Bergson ended up writing a complete book called Duration and Simultaneity against Einstein's theory of relativity. And the book had been in production. He had studied for more than a decade Einstein's work. He had attended one of the lectures of Paul Langevin in Bologna. That was one of the first ones to discuss this twin paradox. And the book would appear a few months after their debate at the end of the year 1922. That year also Einstein received his Nobel Prize. And he had been hoping to get the Nobel Prize for many years. He had even promised to give the money of the prize to his ex-wife for alimony. But when he received the prize, he didn't get it for the theory that had made him famous, for the theory of relativity. He got it mainly for his work on the photoelectric effect and also for his work on Brownian motion. And the presenter of the Nobel Prize was very explicit, and he said that the reason why the prize was not given for relativity was because the philosopher, everybody knows that the philosopher Bergson had contested his theory in Paris, and that the verdict towards it being right or wrong was not an experimental verdict. It wasn't an experiment that needed to happen. That had happened with the Eclipse expedition. If one was looking for an experimental verification, one could have said that happened. The Michelson-Morley experiment had been done decades before, but the presenter said that the verdict had to be epistemological, so that we were looking for a solution that was not technical in order to know if scientists should adopt or not the theory of relativity. And there's a lot that has been written about the experimental verification of Einstein's theory of relativity, and I absolutely do not contest it. But at the time, there were many scientists, the most important scientists to have worked on this topic, mainly Henri Poincaré and Henri Lorentz, had looked at the same experimental results and said, yes, this is true, and what Einstein says is true, but we do not think that we need to completely revolutionize our everyday notions of time and space. We can explain the bending of light by gravity. We can explain time dilation. We can explain length dilation in the same ways that Einstein and the experimental physicists are explaining it. But let us not abandon the way that we think about space and time in our everyday lives, and the way that, because that makes sense for us. And as many of you know, the way that Einstein explains space and time has some real paradoxes. There's some issues that are very hard for us to wrap our heads around. And Einstein did not care about those. He said, basically, the way that we experience the flow of time is an illusion. When his friend Michel Besso died, he wrote a famous note to his sister saying, that for the physicist of faith, the difference between the past, the present, and the future is nothing but a persistent illusion. So it was due to our sensorial limitations, but if we thought as physicists, if we used mathematics, according to Einstein, we reached this other theory of space and time, in which space and time were 4 dimensions. They were put on equal footing according to the general theory of relativity. And that's obviously hard for us to understand. We can get lost and end up is it 5 minutes? Okay. And end up in the west side and not the east direction. But you will never find yourself lost and find yourself in yesterday or tomorrow, right? So it's for us, there are some genuine differences between how we experience space and time, in addition to these other paradoxes, particularly the twin paradox. And I won't say a lot about it, but it's this famous example that you might remember from high school, in which if you have 2 twins on Earth and one of them leaves Earth and travels close to the speed of light, he will have aged less than the twin that stays back on Earth. If they return, he will ascertain that. And Bergson, in his book, wrote about this paradox, and he said, this is the twin that travels is a fictional twin. It's fiction, and that is wrong according to science. So when Bergson's book appeared, the 1922 book, Duration and Simultaneity, Einstein wrote many letters saying that Bergson had made a mistake, and that his mistake had been a mistake of physics. And that represented the moment in which you have the great figure, Henri Bergson, who's a great public intellectual, basically pass off the baton for talking about the nature of time to a physicist. And today, if most of you want to learn about time, you might read St. Augustine, you might read a poet, but if you want to figure out what it is, you probably will go and read Stephen Hawking and read a physicist. So I'm very interested in this change in the authority, the changing authority in who can speak for time. So just to wrap up, because I'm running away, running out of time. One of the things that I wanted to do in my book is I didn't want to write another book about what time was. What is the nature of time? I thought that had been done a lot. But I wanted to write a book about who has the authority to speak for time and how do we as a community, as a society, give that authority, and how is that authority sustained through building certain professions, certain personalities, and disseminating knowledge in a particular way. So I will end with that. Thank you.
Just go for it.
Amazing stuff. None of that is about Bergson, but none of that is so time is an endlessly fascinating subject. Everybody thinks about it, and I've been so many talks on it. I even took the trouble some years ago to buy a special tie for occasions like this. And people, of course, always want to know, could I go back in time and fix up those exam grades, or decide not to date that girl who seemed so nice at the time? And we use expressions like, I will love you till the end of time. The end of time, what's that? Is there an end of time? Could there be a beginning of time? What about God? Outside of time or eternal? What does that mean? What does eternal life mean? Forever and ever and ever? So we bandy these terms around, but I'm a physicist, so I want to bring some precision into this discussion. Now, I first got interested in the nature of time in a previous millennium. It was actually 1967. I went to a lecture at the Royal Society in London by Fred Hoyle, the British cosmologist. And what Fred said was that if a radio station transmits a program, then the listener gets to hear it a little bit later when the radio waves are propagated. Never a little bit earlier. But the laws that describe how radio waves move, Maxwell's equations, are symmetric in time. They make no distinction between past and future. And so according to the laws of physics, there's nothing wrong with listening to a radio program before it is transmitted rather than after. And the question in Fred's mind was, how do we resolve what seems like a paradox? But in daily life, we have this overwhelming impression of an arrow of time, a directionality of events. The future seems different from the past in many ways. With a movie or any everyday scene, play it backwards, everybody laughs because it's so obviously preposterous. What is it that breaks that symmetry of the underlying laws and gives an arrow of time to the everyday world? I want to come back to that because I'd like to actually start with a deeper question, and in many ways a tougher question, which is, did time have a beginning? Was there an origin of time? I think about the end of time. What about the beginning of time? Does it stretch back to ever and ever in the past? I used to lie awake as a teenager worrying, well, if it's time has gone on forever, why am I living now rather than at some other time? And you must all have had these feelings. Well, these days, we tend to think of the origin of time in connection with cosmology, the origin of the universe, the big bang that started it all off. And when I was a student in a previous millennium, the party line was that the Big Bang was the origin, not just of matter and energy, but of space and time as well. That is, that there was no time before the Big Bang. The Big Bang was the beginning of time. And if I discuss this at dinner parties, people say, oh, but that's a trick. Something must have happened before the Big Bang, or there must have been something going on prior to this. There must, time couldn't have begun then. This is just play on words. But actually, Augustine in the 5th century already said that the world was made with time, not in time, and he wasn't the first person to say that. So the idea that time itself comes into being with physical reality, with the universe, that's a very ancient concept. And it's one that is, according to the simplest version of modern cosmology of the Big Bang Theory, that's what happened. Now, I don't have time to get into it, but you can sort of unpick some nuances. You can say, well, why did time just switch on like that at some arbitrary moment? What was it that caused that to happen? Can we make sense of that? And I should just say in passing that Stephen Hawking and James Hartle developed a theory in the 1980s where time is bounded in the past. It doesn't go back forever and ever, but there was no particular pertinent moment, no event, no singularity of which things switch on. And the reason for that has to do with quantum physics. I can't get into it now. Maybe in the tutorial that follows this, we can unpick that a little bit. But I want to emphasize that in the simplest version of modern cosmology, the Big Bang was the origin of time, and asking what happened before the Big Bang is, as Stephen Hawking put it, it's like asking what lies north of the North Pole. And the answer is nothing, not because there's some mysterious land of nothingness north of the North Pole, but because there ain't no such place as north of the North Pole. For the same basically geometrical reason, there ain't no such time before the Big Bang. It's not the time. So to say the universe came from nothing, as my esteemed colleague Lawrence Strauss does, doesn't mean there was some sort of nothingness sitting there waiting to make a universe. It means that there was no place, no time, no thing prior to the origin of the universe. I have to say that in the last 20 years, opinion among cosmologists has swung to the idea that maybe reality is eternal, and that what we've been calling the universe all along is nothing of the sort. It's just a fragment, a component it's just one bang among many scattered throughout space and time, together forming a multiverse which is eternal. So you get the best of both here. You have an eternal multiverse, and you have individual universes with births, lives, and maybe death at the end. I'll try and say a little bit about the end of the universe. So that's the currently fashionable view. To be honest, we don't know. Fred Hoyle, incidentally, liked the idea. He coined the term Big Bang, but he was a skeptic of it. He thought the universe was eternal, had no beginning, will have no end, and that as it expands, new matter is continually created to fill in the gaps. Evidence shows that that is really not the case, but it was an early heroic attempt to solve the problem of the origin of time. So let me now move on to this subject of time travel that everybody's fascinated by. People often say, well, can we travel in time? Could we travel in time? In principle, is it possible? And my answer is, not only is it possible, we've done it. We've done it already. In fact, we're doing it all the time, traveling in time. It's actually very simple to explain. But in daily life, and maybe this is Bergson's problem, we tend to have this idea that there's the time, there's sort of common time throughout the universe. But what Einstein showed is that time is relative, that your time and my time are not the same, because we can get out of step, and we can get out of step in two ways. One is by motion. I already mentioned this, often called the twins effect. If I get on a plane and I fly to London and then come back again, my time and your time have got out of step by a few nanoseconds, and that's easily measurable with modern clocks, has been measured with modern clocks, and no doubt that this is true. In fact, the global positioning system, which at the moment is being compromised by some military exercise, according to sources that I won't disclose, makes fundamental reliance, as somebody didn't turn that right off, fundamental reliance on this time warping or time shifting effect that Einstein predicted way back in the early part of the 20th century. One way that time can get out of step is The other way is gravity. Time runs a little bit faster up on the roof than it does down in the basement. And again, you can test that. You put a clock in space, compare the ticks with the clock down here, easily measurable. They get completely out of step. The GPS wouldn't work if you didn't factor in both of these effects. So we know that they are real. But in both cases, what this is doing is getting you forward in time. So the traveling twin or the twin that goes into a deeper gravitational well, say stays down here on Earth, is traveling a little bit into the future of the other twin. Now, we're talking nanoseconds here, billionths of a second, not such as to make a Doctor Who type adventure. But you could leap years and years into the future. You could reach the future quicker by traveling much closer to the speed of light, or by going closer to the surface of a black hole. Where at the surface of a black hole, time literally stands still relative to a distant observer. So we know these time warping effects are real. We can measure them, and they have the effect of enabling any individual with enough money to be able to get to the future quicker. For example, if I go off at very close to the speed of light to a nearby star, come back again after 2 years of my time in the rocket ship, I may find 20 years has elapsed here on Earth. That's the King's effect. This is arbitrary numbers. You can have any numbers you want. In effect, I will have leapt 18 years into my spare future. But, and this is the big but, you can't go back again. You can't repeat the out and back, get back to the time you left. So going back in time is much more problematic. But there's nothing in Einstein's general theory of relativity to forbid it. Now, there may be other aspects of physics that rule it out, but our best understanding of space and time is the general theory of relativity. And it says that, in principle, traveling back in time could be possible. And many of you will know, when Einstein fled from Nazi Europe, made a home in Princeton at the Institute of Advanced Study, where he was one of the early employees there. And he used to say the only reason he went to work was to walk home with Kurt Gödel, the Austrian logician, slightly crazy character, very eccentric, and he was a logician and a mathematician, but he was captivated by the idea of being able to travel back in time. He found a solution to Einstein's general theory of relativity that permitted an observer to go off, not just to go anywhere in the universe, but to anywhere. Well, moving back into this observer's own past. And Einstein was deeply troubled by that. He really didn't want unrestricted time travel of that nature in his theory. But it's a perfectly good solution, and it is not being ruled out, and there are other solutions to it, involving wormholes and whatnot. I'm not going to get into all that, but certainly Kurt Gödel himself was very excited by the prospect of this. Freeman Dyson tells me, who's now in his 90s, there was a youngster at the Institute in those days who used to say that Gödel was often coming up to him saying, "Have they found it yet? Have they found it yet?" He was referring to the rotation of the universe. If the universe is rotating, we could do this time. Now, I'm running out of time, so I'm going at a fast pace. I wanted to now reconnect with the story of the arrow of time, because that's where we get into the most vexed territory. And if Jimena and I fall out this evening, we could probably be on this topic, I don't know, we should see, which is that we have this everyday overwhelming impression that time is flowing or moving or passing. There are many metaphors, like a river of time. It's something that is absolutely fundamental to the way we perceive time. We think of there being a present moment, a now, and that this now is somehow marching forward into the future. And this impression is overwhelming. And the problem is that in physics it makes absolutely no sense whatsoever. Let me stick my neck out and say, I think, along with Einstein, Jimena already quoted him, the past, present, and future are only illusions. If that's correct, time does not pass. It's meaningless even to talk about time passing, because, as Marcelo said, it does seem like time is speeding up, because it used to be an awful long time until Christmas when I was a child, whereas now, I say to my wife, there's Christmas next week. We haven't taken the past. And so we talk in this sort of flowing time language all the time, but it makes really no sense because how fast does time pass? I'll tell you, 1 second per second. But that doesn't tell us anything. The idea of something flowing or moving only makes sense if you have another time against which to gauge it. We can talk about how fast does a ball move, how many meters does it go in a certain interval of time, but time itself can't move. Time itself can't flow. I think I know where this confusion comes from. And let me just very, very briefly say that when we say all my life, it seemed to me that time is passing and that this present moment is a special moment. We're assuming that the self, our personal identity, is conserved. That, okay, I may change my opinions or my tastes, but it's still the same me, always has been, right from birth. And so this me is experiencing different moments in time and time pose and time. Well, it's back to time. What's changing is not time. It's me that's changing. Tomorrow's me is slightly different, only very slightly, from yesterday's me. And so time itself is just there. It's the me's that are changing. So later me's are different from earlier me's. Each me at each instant is correlated with the state of the world at that instant. And we mistakenly think of this as time flowing or moving. Time doesn't. Time, like space, is just there. You unfold the time state like you unfold the map of the territory, the landscape. And physicists just think of space-time as simply there. Nothing happens. There are simply later moments and earlier moments. There's certainly an arrow of time, that is a distinction between earlier and later. That's quite a different thing from the flow of time. And in literature and a lot of philosophy, I have to call it bad philosophy, conflates these two meanings of the word arrow. But the arrow can mean you fire an arrow and off it goes. It's motion. But there's also an arrow on a compass needle or a weather vane. It simply points in a direction. And when we talk about the arrow of time, it's simply pointing towards the future. It's not moving towards the future. So people should stop using this term arrow of time to mean this illusory flow of time. And yet it's so deeply embedded in our culture to talk about time flow, leading to I liken the illusion of the flow of time to dizziness. I could do the demonstration. You stand up and you twirl around like this, and then I get this overwhelming impression that the universe is rotating. Well, it's not rotating, because I can see it's not rotating, but it feels like it's spinning. In the same way, it feels like time is surging forward. But when I stop and think about it, what's it come from? It's myself that is later moment. And so I think the illusion of the flow of time has something to do with the way the brain lays down memory and so on. And we can get into all that with psychological perception of time, if there is time. How much time do we have? I'm probably out.
Yeah.
I've been talking very fast because there's a lot to say on this subject. Heaps of things I've left out.
We'll get back. Yeah, right. Thank you so much, Paul. That's great. We need days, at least, to discuss this. So, are there any questions you'd like to ask one another before I ask you questions?
Yeah, just one question about your when you say that you're changing, so it's not time. What is changing in you? So are you saying that there's like a hidden something time sort of?
Right. So because we have this sense of self, we are under the illusion that these selves are like sort of conserved entities. And although the selves may experience different things, including about one's own personality, but there's sort of some inner core of meanness which is unchanging. But really, selves are just the sum total of all our experiences and introspection and so on. And that every day, that's a little bit different. So the technical way of expressing this is very high mutual information between today's Paul Davies and yesterday's Paul Davies, less mutual information between the 5-year-old Paul Davies. These are different entities, and they have different mental states, and these mental states are correlated with physical states of the world. And at each instant of time, there is a mental state, a physical state, and a Paul Davies in 1946 and a Paul Davies in 2018 or whatever it is, and hopefully some Paul Davies in the future too. And that's all there is, and that everything about the world could be expressed in completely time-neutral terms. We make no reference to time passing or flowing. Every statement that you make that refers to a flowing or moving or passage of time could be recast in careful, rather boring, unpoetic language without making any reference to that. And yet, even some physicists simply don't believe that, and many philosophers don't. I was strongly influenced by J.J.C. Smart, the Australian philosopher who did more than anybody else to sort of demolish the idea that time is flowing or moving. But tradition of physics really begins with Einstein and Hermann Bayer. Now, I'd be interested to know your point of view. But of course, in daily life, we all sort of feel time is moving. But if you, as a philosopher, examine that, what do you think?
Well, yes, that was at the crux of the debate between Einstein and Bergson, and Einstein holding this idea of a block universe, Minkowski and Hermann Weyl adopting that, and that being, as you say, very absurd when we think about our daily lives. I think in my book, and Bergson had the opposite view. Time was the heterogeneous. It was the eruption of the absolute new. It was indeterminate. So it wasn't just a recycling of bits. So you could not have like a statistical thermodynamic interpretation of the arrow of time in his view, because that's still also just recycling. It was really the rupture of novelty into the scene of life. And he was a very arrogant philosopher, and he looked back and he said, before me, for the previous 1,000 years, everybody's been talking about things being static and fixed. Yet, in our daily lives, poetry, music, our concerns, our feelings, everything else in her world is completely motivated by the opposite. It was a very simple statement. He had to go back to the Platonists, to Plotinus, to find some allies in Greek philosophers, Heraclitus. He wrote a book against Darwinian evolution, because the way that it was described by Herbert Spencer was also, there was evolution, but it was just the recycling of the bits of matter already there. It wasn't the real creative evolution, and Bergson was, we've missed this, and this is science. It's wonderful. It's utilitarian. It's led us to do these wonderful machines. It has led us to be able to predict astronomical events, eclipses, but it does not explain our basic reality. And I don't in my book I don't take sides for the block universe or for a Bergsonian. In fact, when quantum mechanics came back and with indeterminism, Bergson and some of his allies said, well, it wasn't Bergson that was wrong on the science; it was the science that was wrong on Bergson at the time. So as you say, this is even a debate within scientists. There are contemporary scientists, some of your colleagues, Lee Smolin, Adam Frank, that have found Bergson and some of the continental philosophers as inspiring. And just to conclude, my point of view is that it's a real tragedy, and that it explains the 20th century. It explains this division between the sciences and the humanities, between the arts and the sciences, between the world of experience and the world of rationality that is representative of a divided century, and a century that has been very violent, and a century in which there are large groups of people, large groups of intellectual spheres that simply don't talk to each other, that there are silences in universities between the humanities and the sciences, between the arts, and that even our own experience is in a sense divided when we talk about these things, when we think about them. We jump into certain registers. Now I'm talking about objective time, and now I'm talking about how we feel them. Movies, the cinematographic camera, I think, is one of the instruments that embodies these contradictions. In a sense, the frames are all equidistant. They have the same time frame, but the way that the stories are told jump back. There's flashbacks. There's premonition. There's hardly a novel that is strictly chronological. In fact, there's hardly a science book about time that is chronological. So this division, instead, my point of view, instead of citing in one sense of the other, is to see how it has been representative of the 20th century as we've come to know it, and to hope that perhaps we can move to a different type of dialogue.
Yeah, there's a complication that came up after the debate, right, which is the discovery that, as Paul was mentioning, that the universe itself has a history, and that there is a sense of a cosmic time, which is the cosmological time, which is really a universal clock, in a sense that you can go out there and you can measure the distance between two galaxies, and they will move apart if they're sufficiently far apart to begin with.
But you need to explain that at any given point in space, it's just one reference frame.
Right.
And that's the frame in which the observer sees the cosmic background heat radiation uniformly distributed. And that defines at each point in space a unique reference frame, but it's different from the reference frame over there and moving apart with this time of the universe. It enables common time coordinates to be applied across the universe, which is why you can make statements like a Big Bang was 13.8 billion years ago. That's in reference to that cosmic time and not time as might be told by cosmic rays.
Well, definitely. Yeah, but that's kind of interesting, because then that tells you that the universe itself has changed, and you can tell a story.
Yeah, you can, absolutely.
Right?
And this is and so this here, we're back to this distinction between the arrow of time, which is certainly objectively there. Nobody would say that the universe is unchanging. Later states of the universe are demonstrably different from earlier states. It's bigger now. So, it's cooler. The entropy's gone up. There are all sorts of ways in which the universe is changing, and that is the correct arrow of time. But nothing sort of flowing or moving or anything of that sort.
Right. That's a full figure.
The most distinguished scientist that I ever met, who was convinced time was the passage of time is an intrinsic property of time itself, not a property of the world, was Ilya Prigogine, but he was a chemist.
That's true. He was a chemist. Yeah.
We used to often debate.
And he and Isabel Stengers wrote about the Einstein Bergson.
That's right. Yeah, they did. So I knew very well. Exactly right. But we didn't fall out of it.
Do you want to mention something about time and matter asymmetry? Because I think that's very important, and we haven't talked about that.
Matter and antimatter asymmetry.
Yeah.
Yes.
Yeah.
Well, there's a theorem which better be true in almost any sensible fundamental theory of physics, called the CPT theorem. And what that means is that if so when we talk about the arrow of time, we're thinking of an arrow or direction. If you flip it, that's time reversal. That's often given the letter T. What it means is that in the laws of physics, wherever T time appears, you put minus T. That's what that's all about. The other one, C, stands for charge, and that means if you've got a positive charge, the C operation would turn into a negative charge. So proton would turn into an antiproton, and electron into a positron. And P stands for parity. That's right-handed, left-handed. So in a mirror, the laws of physics, do they look the same in the mirror as not? Turns out that they don't. And so the theorem says if you combine all three together, then collectively they must be respected. So if you reverse charge, parity, and time, everything should be the same. That is, that the laws should be invariant under CPT. But not necessarily under individual components of that. So the matter-antimatter asymmetry really is like the CP bit. If you reverse that, you can matter and antimatter. So if CPT is conserved, if T were to be violated, then CP would be violated. And that's a very attractive prospect, because one of the big mysteries about the universe is where is all the antimatter. So we can make matter in the lab easily, done every day. But whenever you make matter, you make an equal quantity of antimatter. You make a proton, you make an antiproton. You make a proton, you make a positron, so on. So the Big Bang had plenty of energy to turn into matter, and we're made of this matter. What happens with the antimatter? And the feeling is that there must be a slight asymmetry between the laws of matter and the laws of antimatter. So in the early days after the Big Bang, there was almost equal quantities of both, but a slight preponderance of matter. And then the matter and the antimatter annihilated and made all the photons that gave us the heat of the universe, and this sort of leftover residue of matter is what the universe is made of. So it's a really important thing. But that goes with a concomitant reversal of time. So I said earlier on at the outset that the laws of physics are symmetric under reversal of time. That's true of the laws that govern electromagnetic waves, and it's true of almost all everyday phenomena, but it is not true of some subatomic radioactive phenomena, namely the weak interaction. There's a slight breaking of the symmetry between time forward and time backwards. It shows up in very careful particle physics experiments. It doesn't affect the fact that when you stir your cream in your coffee, it mixes up, and you keep stirring, it doesn't unmix. All that's left alone. So that the level of fundamental particle physics is this very curious slight time asymmetry, without which probably we would not be here, because it's connected in some ways, not still completely worked out, with this CP matter antimatter.
Okay, great. Hey, Jimena, do you want to mention something about, you mentioned authority and who has the authority, and that was one of the most important things in the book. So who has the authority to define time and why?
Well, you know, the debate between Einstein and Bergson was the important, historically speaking, you know, the important moment in which we see the reversal. Physicists starting to take on that role, and that role has only accentuated. Nobody would think that, you know, an artist or a poet or would go to an artist or a poet to find the truth about time. The role of the philosophers and the humanists have been sidelined more than ever. An important paper was Hilary Putnam, a philosopher who was my teacher. Once he wrote a paper in 1967 where he said he basically repeated the point that the problem of time, that philosophy had nothing to say about the problem of time, and then a lot of things that he wrote afterwards contradicted that early statement, but it was a very important a moment, and we have these continued comments in the public sphere from Neil deGrasse Tyson to Feynman that continue to claim that philosophy has nothing to say about this issue. Feynman said that philosophy was as useful to physicists as ornithology is to birds, and I think that it's pretty. I mean, I think it's very unfair. But it's still pretty clear. You know, if you have seminars about the nature of time, you're going to have a physicist, somebody like Paul Davies, that's what as a society we have given the authority to talk about the nature of time. And what's interesting for me about that is that continues when there's a clear contradiction in the time-telling techniques used by ourselves in our narratives, used by filmmakers, used by novelists, and what to do with that division, right? That's what I find interesting.
In defense of philosophy, just last week I went to a talk by Frank Wilczek, one of our colleagues in the physics department, called 14 Mysteries of Time. And so he convinced the listeners that the last word has not been said on at least 14 aspects of the nature of time. And so I think that physicists can give a pretty reliable account of all sorts of things about the nature of time, and there are experimental tests that we can do, as I've already mentioned. But there are still open questions about the nature of time. I'm not, in spite of my evangelizing about time does not pass, I still don't feel entirely comfortable. But I wrote an article once that it's an illusion. If time, the first time is an illusion, it's an illusion we can't afford to give up. Like free will, again, in many sciences and philosophy, there's a thing as free will, but we can't afford to give it up, otherwise normal life would become possible. And these are two connected topics.
That's true. I guess on that note, we should open for Q&A from the audience. Thank you very much to both of you. I think we need microphones, right? Paulina has one over there. Excellent. So please speak at the microphone because we're videotaping this, so other people can listen as well.
Yes, Professor Davies, a physics professor for me just explained the direction of time as a consequence of the law of entropy, that you just can't create order from disorder. And that always satisfied me intellectually. Is there a reason I shouldn't have been so easily satisfied by that explanation?
Yeah, there are two reasons, actually. But I'll try to keep this brief. First of all, it's clear talking about the second law of thermodynamics. Who is it who showed CPC? Yeah, you showed that video. Right. Of course, he cited that as an example about the chasm between the humanities and the sciences. But sitting at high table in Cambridge, you would be ashamed to say, I've never heard of William Shakespeare. But if you said, I've never heard of the second law of thermodynamics, actually, no. So the second law basically says that the universe is getting more and more disordered or chaotic with time, and that's what gives us one reason why there's an error. There are other errors as well, but that's the most pervasive one. And so the simple statement is that the universe started out in an orderly state and becomes more disorderly over time. That leaves open the question of why did it begin in an orderly state? So the biggest mystery about simply saying it's all about entropy is why is the early universe in low entropy state? And it's further compounded by the fact that when we look at the early universe, it doesn't seem to be an orderly state. It seems to be a maximum entropy state, a state of thermodynamic equilibrium, because the background radiation, the fading afterglow of the Big Bang, has a time spectrum. So matter and radiation were actually in equilibrium at the beginning. What was out of equilibrium is gravitation. And the gravitational aspects of entropy have still not been worked out. It's still very much an open subject. Then there's another issue, why it's not quite so simple as to say entropy did it, which is, as John Wheeler used to like to say, if you ask an atom the direction of time, it will laugh in your face. They had this term of phrase. What that means is, at the level of individual atoms, there is no time forward or time backwards. It's a collective. Entropy is defined as the behavior of collection, large numbers of things. And just to give you a simple example, if you take a deck of cards, which is newly purchased. It will be all ordered, suiting numerical order. If you shuffle it, it will become disordered as a result. And then you think, well, if you keep on shuffling, will you get back to that original state of order? In principle, yes, you'd have to shuffle for a very long period of time. But if you look at an individual card, the notion of order or disorder is irrelevant, it's only in relation to the collection. So that seems to make time, the arrow of time, a somewhat subjective concept. It has to do with our horse-grained view of the world, the fact that we don't see individual atoms. But if you were Laplace's demon, you could see every atom. As Laplace said, the past and future would be forever, present will die. Interesting theological issue. God is all-knowing, is omniscient, knows every atom. Then God has known of the flow of time. So we know something, or God doesn't. That's something the theologians say.
Okay. Yeah, I have a question for there's a historian on the panel. I was intrigued by your comment about Einstein's view of philosophy at that Bergson debate, because his 1905 paper on the electrodynamics of moving bodies seems to me to be entirely a philosophy paper. He makes no reference to experimental data and is motivated entirely by a very aesthetic imbalance in the laws of electricity and magnetism. So did he change his views over time? Was he aware of this change in his own behavior towards sort of more philosophical questions?
Yes, that's a great question. So Einstein definitely had an implicit philosophy, and most scientists have an implicit philosophy. And the implicit philosophy of most scientists is materialism and reductionism. So when you read some of the scientists that want to push philosophy away, they themselves have a philosophical view, but it's implicit. If you study philosophy, if you study history, you can place them within certain philosophical schools. So Einstein's reaction against philosophy at that time was really a reaction against the authority of Bergson and the authority against other people who previously had the right to speak about time and who were the go-to persons for thinking about time. And that during the debate, he said things that he would never say again. So for example, he would say that his definition of time was the only objective definition. And then later on, when he was older, and then he would continue to say that metaphysics had no place in science, that philosophy was subjectivist, and that there had to be just technical answers. And as he grew older, he actually recanted and changed that position. At the beginning, he was also very inspired by the philosophy of Ernst Mach, that was very operationalist, very much based on actual sensations. And then he said, it's sterile. And he thought that the logical positivists, some of the philosophers that had actually jumped on his defense and used relativity as an example of the best types of science that can be done, they had pushed away metaphysics. And he said, no, we actually need metaphysics, and that the difference between physics and metaphysics was actually of degree and not of kind at the end of his life. So he definitely changed.
The later Einstein and the earlier. Not the same person.
No.
Different mental states.
So the Greeks had this concept of kairos and chronos. And is Bergson's duration and the distinction between that Einstein's time, is that sort of the subject and object difference?
That's how it was broadly understood. Bergson was seen as defending a subjective notion of time, but Bergson denied that characterization of his own philosophy. He was interested in the point de capitons, at the moment in which the objective and the subjective tied together. And he thought that it was absurd to think that there was just something objective. So, for example, when Einstein defined time by a clock measurement, which makes a lot of sense. We have clocks. Time is what clocks measured, and he said, 7 o'clock is the pointing of the needle of my clock to 7, and the train arriving at the station. Bergson responded, why are clocks made? Why are they bought? Because we have a prior notion of time. We care about events. We want to go places. And he thought that it was therefore absurd to define a time via clock time. The other interesting thing is that when you look at Einstein's correspondence and his private writing, he's obsessed about time passing by in the same way that Bergson describes it. So he's always running out of time. He's a person that's really, really busy, and it's really an obsession. It's it's in certain years, pretty much in every letter. He calls it the old tune, the old refrain that I don't have time. So inside Einstein himself, there is that contradiction between the objective and the subjective.
Any more questions?
I have a question for Dr. Davies. So I've always construed of time as something that very much needs to be defined in terms of other quantities like velocities of particles or even just motion itself broadly. But it seems like we don't need to do that for fundamental quantities like charge. In your opinion, is time fundamental, or is it better understood as a useful fiction?
Yeah, very good question. So we certainly treat it as fundamental in, for example, Einstein's general theory of relativity. Space and time are just there. Space-time is not an arena. It's part of the drama of nature. It has the dynamics of its own gravitational waves and equals in empty space-time. So it's simply like the substrate of the universe. So you take it as a fundamental quantity, but there's a long tradition of people who feel that time, indeed space-time, might be an emergent property. The proponent of that, who most influenced was John Wheeler, I already mentioned his name, and he had vague ideas what is the pre-geometry. He felt that the analogy he used was with a block of rubber, it looks like continuous, it can be warped, just like space-time. But that if you go down to the atomic level, you'll see that there are some atoms that are bound together. The notion of a continuous medium breaks down. But in the same way, space-time might have some components, some elementary entities out of which space and time emerge. Roger Penrose had something similar. There's actually been many, many attempts to sort of have space-time coming out of the theory. String theory started out that way. Didn't want the strings wiggling around in a pre-existing space-time. Wanted space-time to emerge from the physics of the theory. Hasn't happened yet. So in terms of what do I think probably, yes, we need a more fundamental concept now that we build space-time matter. And indeed, I would say even things like observer. We somehow incorporate that, which ties into consciousness. It's all got to come out of something.
Good. One more question?
Oh, yeah.
Okay.
I actually have a question for Professor Davies. Firstly, I'd like to say that please ignore my lack of information on this topic, but I have 3 questions. The first thing, as you mentioned that there was nothing before the Big Bang. A question was there was something that caused it, and things that caused it must have taken some period of time before causing it. So what do you mean by that? Right. Second question being that if time doesn't move, then what does every single tick on my clock suggest? And the third one is, as you said, the time is static, it doesn't move. Then can we imagine time to be a spiral track on which we or the world moves? Because I come across 1 a.m. every single day, but that 1 a.m. is not the same as the 1 a.m. that I had yesterday.
Right. So, I mean, the simplest one is that clocks measure intervals of time. They don't measure the flow of time. So clocks are telling how long between this event and that event, but it's got nothing to do with time flow. So that's what we're talking about. The fact that it goes around like that just for convenience. No reason. Dates, that's time. They just limit. As far as causation, the word cause in normal, in daily life, effects follow causes. If we're talking about the cause of the origin of the universe, it's rather meaningless if there is no time. So the better question is, how is it that a universe can come into being? How is it that space-time come into being from nothing? Well, if the laws of physics permit it, then that's an explanation. It's not a cause, it's an explanation. But then we're driven back to ask, are the laws of physics within time, or do they transcend space-time? Did they come into existence with the universe, or do they have, like mathematics, an independent existence? I've written very extensively on this, carefully unpicking all of this stuff. I created a book called The Goldilocks Enigma, Why is the Universe Just Right for Life? Please may I refer you to that book where all of these aspects are discussed very carefully in easy language, because people get a terrible muddle about words like cause and it.
Our last question. Go ahead.
How do you think the perception of time relates to the size and metabolic rate of the organism or the observer of the time?
Good one. Do you want to do this?
No, go ahead. It's a science question.
Well, there's a scaling law. And so little things live fast and die young, like the mouse, for example. Elephants are more ponderous. They're sort of in the middle. You get a certain number of heartbeats. Exactly what. So the fact that the mouse is scurrying around, is it seeing everything sort of like a fast-forward movie? Of course, we can't know. But it's what we can know, and here we're getting more into the sort of the physiology of the neuroscience, is response. And so I was going to then say, in case there's an opportunity to ask, I once met a man called Miroslav Pulov, who wrote a book called The Duration of the Present Moment. He was interested in music and the way we sort of integrate it all, and the brain, it's not, you don't sort of dissect it. Somehow your consciousness is sort of spread out. I think he said, 1.3 seconds. So forget your tenth of a second, you want to do something longer. But if you look at tennis players, the speed of the ball, there's no way they can think the ball's going a bit to the right, I'll step over there, I'll do this, easy back. It's all happening much faster than the speed of thought. Hence, much faster than the speed of thought. So somehow, this perception we have of, if you like, the flow of time, or at least the succession of events, is a narrative that the brain reconstructs after the event. And so we think of, come back to this idea, we think of ourselves as a unitary entity, a self, me inside, all this sense data coming in, and this is what I'm conscious of at this moment. There's a conscious experience at this moment at the end of the thing. It's all a fiction. When you do the experiment, what you find is that the brain is editing various drafts. It goes back and reconstructs, sometimes reverses the order of events. You can do experiments where you ping somebody's brain to make them feel that this finger's being pricked, and then with that finger to decide, and then you prick the actual other finger, and you can show that the conscious subject reverses the order of the experience. So there's an awful lot of editing going on inside. So heaven knows with the math how much editing is going on, of what it's is it really, can it make split-second decisions? Could it play tennis better than a tennis player? I don't know. There must be some people.
Okay, last question of the evening. Better be a good one.
Whether or not there's a flow of time, is there some experiment that you would do that would?
Well, what could there be? Suppose you woke up tomorrow and somebody said, a terrible thing happened in the night, time doubled its speed. It's like saying we're all twice as big, but so is the universe. There's nothing.
In principle, you can't do
No, sorry, because you have to relate it to something else. You have to say, here is something that measures the speed of the time we know and love relative to some other time that we haven't yet discovered. We could do that. There was a book written by somebody called John Dunn many, many years ago, in which he called Experiment with Time, in which he said there must be another time the time, our time, against. Otherwise, the first time would be another time. But then maybe there's another time for that, and another time for that. So get into the infinite as well. I don't think these ideas are very helpful. I think, come back to what's changing is not time, it's us.
All right. Well, thank you very much for coming.